My name is Nathan Sturtevant, and in this talk I'm presenting my AID 2020 paper on the unexpected consequences of incremental design changes. This is joint work with Nicolas Decroocq, Tripodi, and Matthew Guzdial. In this talk, or in this paper, we're going to be looking at incremental design changes in the game of SNAKEBIRD, so I'm going to begin by showing you some of the rules of that game. The goal of the game is to get your SNAKEBIRD into the exit, which you do by moving into this moving pentagon in the corner. When you're doing so, in order to do that, you first must eat all the fruit on the level, which in this case is the purple grapes. And when you eat the fruit, your SNAKEBIRD gets longer. The other thing we would note is that there are obstacles in the way, like spikes, and if you fall on the spikes, then your SNAKEBIRD will die. And so together, all of these pieces and other mechanics that are introduced in the game make it difficult to get your snakes into the exit. And so this is what makes this game very interesting. Now, if we look at some levels in the game, and we might ask, well, what sort of single change could we make to a level? If that is the question we're asking here, is can it have a big impact? And our hypothesis is that there are many levels where small changes can have a really big impact on the solution to that particular level, but that human designers, especially when we're exploring a new game, we don't necessarily understand the full consequences of these sorts of changes, and therefore having a computer to be able to show us what these possible changes are will help us to understand these things better. So in this first piece of work that we're doing here in this paper is we are looking at the question of, are there incremental changes which make a significant impact? Future work will be looking at the question of how we can use that for designers to help them, or build tools for designers. So in this case, we're looking at two levels. This is level 0 from SNAKEBIRD Primer, and we've made a small change. This is in fact the change that maximizes the change in solution length, which is to add this block in front of the snake. And the solution to the original level is simply to move across here and to go in the exit. And when we make this other change, we put a block, we just change the solution length. And by the way, solution length here is the number of states in the solution path, so it includes the start state. It goes up by 2. And this doesn't seem to be a very important change. It's very inconsequential. But we see that there's other levels, like SNAKEBIRD level 24, where we take the solution length 24, and when we make this incremental change by changing this block into a spike, we see that this level, which of course is more complicated for humans, but we'll see here the computer can solve it fairly quickly. Go ahead and add the spike in, and the solution length jumps up to 58. Now, something that we notice is the first half of the solution is basically almost an independent puzzle of pushing this block around, at which point we get a symmetric solution to what was used on just the first puzzle to get out the exit. And we'll come back to this at the very end of the talk. So we're going to be looking at incremental design changes. I will highlight them in some of the pictures on the sides of the slides, but I'm not going to, they'll be shown there. I'm not going to highlight them in the talk. They're just something that you can look at later. Because this talk is going straight to video, you can always pause and look through those if you'd like to. So we're going to use something called exhaustive procedural content generation in SNAKEBIRD to analyze and find one-step changes that maximize the solution length. And what we will see is that players within the context of our study found the resulting levels to be both more interesting and challenging than the original levels. And again, we'll talk about more about that at the end of the talk. Now, there has been a fair amount of work, and so we just want to highlight some of the work that's been done in procedural content generation for puzzles. We see this in Sokoban, for instance, and we've also seen using answer set programming as a tool for the refraction puzzle games. There's been a fair amount of work in Angry Birds, coming from the Angry Birds competition as well, and there's some very recent work on the game Baba Is You. I think that Sokoban and Baba Is You are particularly well suited for the analysis that we're doing here, but there may be other applications as well. Within exhaustive PCG, this is a relatively new description of a certain type of procedural content generation. This requires two things. It requires a generator and an evaluator. So a generator is going to generate all content, or all, within some parameter. You might be saying all possible parameters within some context, which we'll show here. and then an evaluator is going to evaluate that, and then we just return the very best content according to the evaluator. So in SNAKEBIRD, the generator is going to be looking at all possible locations on the map, all X and Y locations, and we're going to be generating the possibility of changing each tile independently, either to sky, ground, or spikes, depending on what it is already. And we're only going to think about the sky, ground, and spikes tiles, so we're going to ignore things like the exit. We're not going to change those. The evaluator is going to perform a breadth first search and then measure the optimal solution length. And we could choose the min or the max here. We're primarily interested in the max, but we'll also look at the min. And I'll say a little bit more about breadth first search in a few slides. So if we want to make this concrete, so here's a certain level within SNAKEBIRD, and what we're going to do is we're going to go over all X and Y locations, and we're looking at what happens when we change each of these tiles to be a different type. And after we've gone through all of these, we'll come back and say, well, this is the change that maximally increases the solution length, changing this one tile into a spike, and then takes the solution length from being 37 moves long in the original puzzle to actually being length 65 in the modified puzzle. Okay, so we wanted to analyze the game levels that shipped with the game. We put all of them into our analyzer, and 129 of these could be solved easily of the different difficulties, where easily means we could do it within 1 million node expansions. Now, there are 2 levels that our implementation can't handle because there's too many objects in them. But of the 127 levels, then, most of the levels that we couldn't solve can be solved with either additional time, or if we were to build better heuristics, or we were to be able to handle some of the symmetries that exist. But we had enough levels, 108 here, that we didn't implement those changes in, although those are definitely a possibility. And now we're asking 2 research questions. One, does incremental EPCG lead to levels that are significantly different? That is, we're not just putting a small obstacle that increases the solution length by 1 or 2, but we're really changing the nature of the level. And then, do humans find the resulting levels to be interesting? And we're going to evaluate both of these. So we're going to begin by looking at the distribution of optimal solution lengths. And when we look at this distribution overall, then this is before applying any changes. I'm not showing the median here. The statistical analysis is within the paper. But we see that if we were to try to minimize the solution length by making a change, there's often one change that makes a level significantly easier. And there's also one change that makes a level, in fact, significantly harder. And if these changes were small, like always increasing the solution length by 2, this would not be statistically significant, but here we see that it is. But this, of course, just says that there are these changes, but maybe players don't find them interesting, so we're going to evaluate that in a user study. Our user study is in our research implementation, which is called ANHINGA, and this is named after a bird, which has a nickname of the snakebird because it looks like a snake swimming in the water. And the instructions that I gave you at the beginning of the talk were exactly the instructions that we gave participants in our user study. And then we gave them 3 levels taken from the game to introduce them to the mechanics of the game. We modified the 3rd level here that we gave SNAKEBIRD Primer Level 5 to put in a spike to make it a little bit more interesting and to teach them about those mechanics, to teach that you can stand on top of fruit. We then chose 4 additional levels from the game. And these were levels that needed to use very simple mechanics because our players hadn't necessarily played the game before. And then we wanted to evaluate how our players did on these levels. And so players were given 2 sets of levels, so 2 of the 4 levels that were here. And then within a particular level, they were given the variant and the original level in a random order. We then asked the players which levels were most fun, frustrating, surprising, challenging, and interesting, and what level did they enjoy the most. And across all 4 levels, which level did they think was best? And they were shown all the levels when they were making these decisions so they could see them clearly. The survey results show that some of these differences are not significant, but particularly the variations that we came up with are considered by the users to be more interesting, more frustrating, and more challenging. And in particular, the best level, 65% of the time, the best level overall was the one that was the variant with the additional changes made to make the solution length longer. Now, there's some limitations to this work. The evaluation is only within the context of the study. doesn't mean that when we say better, that they actually would be better in the game or that we should replace them in the game with the original levels that we have. Also, we're only looking at solution length, so there may be better metrics besides solution length. And finally, humans don't find optimal solutions. So in SNAKEBIRD level 39, the optimal solution is what's shown, this is part of it. Humans typically put blocks into these notches in the wall, but the optimal solution doesn't do that. And so this may impact some of the results here, but there's still a lot of insight that can be gained by doing this analysis. So in conclusion, we've seen that in the game of SNAKEBIRD, the incremental design changes do have a significant impact on the solution. And if you'd like to play with this, there's an online demo available as part of AID 2020, and it will continue to be there. And this is moving more into the mixed initiative or co-creative space. We were answering in this paper the question of, do incremental changes have an impact? And now we have to say, now that we understand that they do, how can we take advantage of that or help human designers with this? To show you one more level here, this is SNAKEBIRD level 19. Here we've made 2 changes to the level. We've added 2 spikes here. And we can watch the solution. We can see how the snakebirds are moving through the level. And we see that initially the solutions are nearly identical. But at this point, the solutions diverge, and they diverge significantly. And what you see is the potential for something like this is that, in fact, instead of creating this as one level with a very long, very complicated solution, what we might want to do is even break this into 2 separate levels where the players have to explore these mechanics separately. So there's a lot of very interesting things that could be done here, and we look forward to seeing what people are able to do within this space.